So welcome everyone to the Wednesday session of MIPT Quant Conference. I am Nikita Kirsanov from MIPT and Aalto University, and I'm one of the organizers of this conference. And today I'm going to be the chair. So without further ado, it is my pleasure to introduce Professor Thomasin from ETH Zurich, who is famous for his works on quantum states and quantum transport in nanostructures. So Professor In, please.
Yeah, thank you very much. And let me start also by thanking you and your co-workers for organizing this conference and for giving me the chance to present our work here. I will talk about few carrier quantum dots in bilayer graphene. This is work in, it's a team effort, and the data you will see today have mainly been obtained by Annika Kurzmann, who is a postdoc in our group, and Chu Yao Tong, a PhD student. And I will also show some data by Marius Eich, who is a former PhD student who now went to industry. We are also very happy to have world-class boron nitride by Kenji Watanabe and Taniguchi in Japan. And we are happy about theoretical support by a group at ETH, František Hermann and Manfred Sigrist, and also by the group in Manchester, Angelika Knote and Vladimir Falco. So let me start by showing a slide which I used to show many years ago, in fact, to highlight the vision of this kind of project. At the end of the day, we want to build qubits made of graphene. And the advantages of graphene have been pointed out in previous works. So graphene is known to have very weak spin-orbit interaction because carbon is light. And we expect to see weak hyperfine coupling effects because 99% of the nuclei are essentially spinless in this material. So this promises long spin coherence times, and this has been pointed out in a number of theoretical works already many, many years ago. We traditionally come from the gallium arsenide field, and in the gallium arsenide quantum dot systems, spin coherence is strongly limited by spin-orbit interaction, hyperfine coupling. And this is why graphene seemed to us to be a very useful direction to investigate into. While many other people are working on silicon nowadays, we try to push quantum dots in graphene. Now, probably most of you know that if you do graphene layers, then you have to fabricate samples, and I will show you in details how we do that, how we realize gate-defined quantum dots. And this is mainly based on work that has been published by Marius Eich in our group already 2 years ago. And then I want to go on and show you more recent results that are not published yet on the tunability of the so-called Valley G factor. And I also want to show you bipolar operation of these graphene quantum dot systems. So when we fabricate graphene devices in general, then we first of all stack many layers on top of each other. And the result are very complicated devices. And I decided to show you, give you a step-by-step introduction into the layer structure of our devices, such that you don't get lost in the complicated final device structure. So we always start on a silicon substrate, which has a thermal oxide on top. This is step number 1. And the first layer to be put on top is a graphite backgate. So this is typically a few 10 nanometer thick graphitic layer, which provides a smooth surface for other layers to go on top. And it also gives us already a high quality backgate for the devices that will be on top. Then on top of the graphite backgate, we stack an insulating layer of boron nitride. That's my step number 3 on the right. And on top of that comes the bilayer graphene. This is the 2-dimensional electron gas we are eventually interested in and where we want to realize the quantum dot in. Now, at step 4, you already have a device that would show the field effect. So we could apply a voltage to the backgate, to the graphite backgate, and in this way tune the carrier density in the bilayer graphene layer, which is now on top. However, it turns out that the device quality would be much higher if we encapsulate the bilayer graphene in another boron nitride layer. So this is what comes on top. There's another boron nitride layer on top, such that the bilayer graphene is now encapsulated between boron nitride. And in fact, this prevents the quality of the bilayer graphene to degrade and results in very high quality devices. Now, in bilayer graphene, and I will show that in a minute, we do not only want to change the density of the two-dimensional carriers, but we also want to change the vertical electric field. We call it the displacement field applied to this two-dimensional electron gas. And this is why we put another gate layer on top. This is typically a gold gate that spans the whole device. And I will show you in a minute how we can then tune the conductivity of the bilayer graphene using the backgate and the top gate together. So the basic idea to make nanostructures in bilayer graphene is based on the possibility to open a band gap in this material. And this happens by applying a vertical displacement field. I call it D here. This is the vertical arrow that you see, the red arrow, which is applied normal to the two graphene planes of the bilayer system. Now on the right-hand side here, you see the band structure close to the K point of bilayer graphene. In the case shown on left, there is no displacement field applied, and you see that there is the conduction band and the valence band dispersion relation that touch in a single point at zero energy, and we have two additional bands which arise in this situation that are further remote conduction and valence bands. Now, applying a displacement field will open a gap at the position of zero energy where the two bands, conduction valence bands, were originally degenerate. And this is shown on the right-hand side. So you see two cases. A weak displacement field would simply open a gap and still leave you with an almost parabolic dispersion. But if you have a stronger displacement field, you get a sombrero hat kind of dispersion relation for the conduction band and for the valence band. And you have a significant band gap of typically a few 10 milli-electron volts in such a situation. Now, once you have a material with a band gap, the hope is, of course, to define nanostructures electrostatically, like we do it in gallium arsenide. Additional advantage do not feel the edges found in the past, and this electrostatic band gap opening and nanostructure definition would allow us to avoid charge carriers of seeing the edges of the graphene flake. Now, such a device would then be measured very simply by measuring the in-plane resistance or conductance of the bilayer graphene sheet while we apply voltages to the backgate and to the top gate of the device. And you see a measurement of the sample resistance in this color plot, where on the horizontal axis we change the top gate voltage, and on the vertical axis we change the backgate voltage. Now the resistance of the device is color-coded, so low resistance is blue and high resistance is red. And please note, this is a logarithmic scale, so we go from 100 ohms roughly resistance up to 10 mega ohms of resistance. And the device is measured at a temperature of 1.7 Kelvin. Now you see in this plane of the two parameters, of the two gate voltages, you see two characteristic features, a horizontal line of enhanced resistance and a diagonal line of enhanced resistance. And these two lines, they correspond to a situation where the Fermi energy is in the band gap of the material. Now you have to see that in our device here, we have three regions, three spatial regions. We have a region that is gated by the top gate, and we have two regions outside the top gate, which are only gated by the back gate. So if the outside regions are tuned such that the Fermi energy is in the band gap of bilayer graphene, then this produces this horizontal line of enhanced resistance. This diagonal line, in turn, is dependent on both gate voltages, and this essentially means this must stem from the region which is top gated also. And we see that we change along this diagonal line the displacement field. The displacement field essentially arises from a difference of gate voltages between top gate and back gate. So if we have a very negative top gate and a very positive back gate, we have a strong displacement field, and this is indicated by this arrow here. And you see the stronger the displacement field gets, the larger is the resistance along this line. We even go into the 10 mega ohm range, so we can make the region below the top gate insulating along this line. And this is exactly the effect that we wanted to achieve. We wanted to be able to deplete the electron gas below the top gate by the action of top gate and back gate together. And this view graph shows you that we can really reach very high resistances, really insulating behavior in the gated region. Now, in order to make progress in fabricating small structures, nanostructures, we now structure or pattern this top gate. So we go from a homogeneous gate that you've seen before to a so-called split gate geometry. So we split this top gate into two parts and leave a gap in between. And within the gap, of course, the electric field, the vertical electric field, will be smaller than it used to be in the homogeneous gate case, such that a one-dimensional channel arises through which charge carriers can flow. So the basic idea is now, again, to measure the in-plane resistance of the device, which you see here again in the same color-coded plot. You see the same horizontal line, which indicates the charge neutrality point of the region outside the top gate. And you see the diagonal line, which is the resistance essentially related to the top gated region. But now, look at the resistance scale. Now we can only get resistances up to kilo ohms, even though we tune the two split gates to voltages where they deplete or make the region below insulating. And this is because there's still a channel, a conducting channel in the gap between the two gates that remains. And in this channel, we have a finite resistance of kilo ohms. Now, for forming quantum dots, of course, we need further control over the electron density. And we essentially want to control now the density, the local density in this electronic channel. And this requires more fabrication. So we take the split gate device and deposit an aluminum oxide insulator on top in order to isolate this split gate from whatever is going on top. Now, what goes on top in the simplest case is a finger gate that spans across the conducting channel that is left between the split gates. And this gives us in the channel a way to locally control below this finger gate the density, whole density. So let me show you a typical measurement now of this channel. the gray edges of the split gate of the two channel in the middle, and we work in a situation where this channel has N-type conduction, and the dotted line, the blue dotted line, shows you essentially the outline of the finger gate that goes across the channel, and we are now looking at the conductance of this channel as a function of the voltage applied to the finger gate. So in this view graph here, you see on the horizontal axis the finger gate voltage, and on the vertical axis the conductance of this bilayer graphene channel. Now at 0 volts, the channel is essentially homogeneous in density, and we get a very high conductance of roughly 4.5 E squared over H. But if we now apply more negative voltage to the finger gate, we start to deplete the region in the channel below the finger gate. So we have a new density, a lower density N prime here, and correspondingly we see that the conductance has been reduced. And so we continue until we reach complete pinch-off. So you see in the schematic here that now the density below the finger gate is essentially 0. The Fermi energy has been tuned into the band gap of the material, and we only have the N-type contacts at the outside that are now separated from each other by an insulating region, and this is why the conductance has become essentially 0. Now, an interesting thing happens if we go even further, if we apply even more negative finger gate voltage, because then we place the Fermi energy essentially into the valence band. We attract holes in the valence band below the finger gate, and now we have an in-plane NPN device. So we have conducting N-type regions, we have a confined P-type system with holes in it, and another N-type contact on the other side. And you see in the measurement, in the measured conductance, we see very sharp resonances here, which remind us, of course, of resonances of bound states in this quantum dot structure here, which is P-type. So there must somehow be a tunneling coupling between the P-type region and the N-type contacts at the outside. Now, in order to understand a little bit how this device really works, let me show you this schematic on the right. So we have the 3 regions, 3 spatial regions. In the N-type regions, contact regions, we have the Fermi energy in the conduction band, and we have a schematic dispersion relation drawn here, where you see how we fill up states to the Fermi energy to get N-type conduction in these regions. Now, below the finger gate, we have a P-type quantum dot. So we have essentially pulled up the dispersion relation such that the Fermi energy is now in the valence band, and we have accumulated holes in this region. Now, of course, spatially, there must be a continuous transition between the P and the N region. So right at the edge of the finger gate, the dispersion relation would be such that the Fermi energy is in the gap of the material. And this essentially forms the tunnel barrier that decouples the states in this P-type island from the N-type leads and gives sufficiently weak coupling that we see Coulomb blockade peaks. And you see that in the diagram here, which is a blow up essentially of the device. You see that we see very sharp resonances, and we can label the spaces between the resonances with a number of electrons. So here we are completely depleted, have no electrons, 0 electrons. Then we have the first resonance. After that, we have 1 hole in the system, then 2 holes, 3 holes, 4 holes in the system. And we can now do quantum dot physics in this device. Now, what we are interested in this talk is essentially to understand the few hole case, the quantum dot with very few holes. And I want to show you that there is an interesting behavior of the states in a perpendicular magnetic field, which we can investigate. So this is shown in this diagram. So we measure now the resonances that you have seen before at 0 magnetic field. That would be in this diagram, the resonances as a function of finger gate voltage that you see on the vertical axis here. That would be these bright lines. These are the resonances we've seen before. We measure them as a function of perpendicular magnetic field in this diagram. And you see that these resonances, they shift as a function of magnetic field, and they go up and down a little bit in finger gate voltage, which at the end can be calibrated into an energy scale. So what we do is we mark the positions of these resonances in this plane of finger gate voltage versus magnetic field, and we subtract between neighboring peaks a magnetic field independent charging energy. And this gives us the so-called single particle level spectrum of this quantum dot that you see on the right-hand side. And this single particle spectrum, which essentially corresponds to a kind of Fock-Darwin spectrum, if you like, for graphene, for bilayer graphene, this spectrum shows interesting structure. So you see that there is a degeneracy of states for the lowest energy states, which is lifted as a function of perpendicular magnetic field. Now, this energy splitting is very strong. And you can very quickly find out that it has nothing to do with spin splitting or Zeeman splitting, because the G factor in graphene or bilayer graphene systems is simply 2, and the splitting that we observe here is much, much bigger. But there's a second degeneracy, of course, in bilayer graphene, which is the valley degeneracy, the degeneracy between states at the K point and the K prime point of the first Brillouin zone. And it turns out, and I will show you more experimental evidence of that, that the splitting that we observe here is in fact a K prime splitting, so a splitting between the K states and the K prime states in a magnetic field. And similar as we do it for the Zeeman splitting, where we define a G factor for the splitting, for the linear splitting in magnetic field, we can define a valley G factor here, which describes the size of the splitting as a function of magnetic field. You also see that there are higher single particle states, some of which run essentially in parallel. So if we call the lower branch here the K prime branch, then this would also be a K prime branch, and this would be a K branch. And you see further K prime branches going down here and other K branches going up here. So even at higher electron numbers or higher excited states of the system, we see the same kind of valley splitting in the system. Just to give you an idea, in fact, about the spin splitting, this is a measurement now in parallel magnetic field, where the valley splitting is absent, and the only splitting of states, and you see the splitting of the lowest 4 states here, is spin splitting, right? So you see these 2 states, the K prime and the K state, which are offset for clarity, with spin down, and you see them running in parallel. But then the spin up states of K prime or spin up state of K, they are essentially moving in the opposite direction. And if you determine the splitting between, let's say, K spin down and K spin up as a function of magnetic field, you find a G factor of 2 as it is predicted for the graphene material. Now, the fact that we have this spin degree of freedom, of course, would make us hope to one day build spin qubits, but having the valley degree of freedom, we have kind of a pseudo spin in the system, which could make us think that we could build valley qubits. And then the valley G factor is, of course, a very important quantity. Now, in order to investigate this valley qubit option a little bit further, we made the device still a little bit more complicated. So we added 2 more gates to the system. You see, we go from a single finger gate device to a 3 finger gate device. Now, adding these 2 more finger gates, we have the possibility to tune with these 2 outer finger gates the tunnel coupling of this PN junction that confines the quantum dot, and the middle finger gate will tune the electron hole number in the quantum dot. So this is now a slightly more complicated device, And here I show you the same splitting of the lowest 4 energy states, the valley splitting now again in a perpendicular magnetic field, for 2 different tuning voltages on these 2 outer gates. And this enables us essentially to create a very small quantum dot on one hand, this is shown on the left, and a very large quantum dot, which is shown on the right. And you see from the splitting of these levels, from the linear splitting, we determine this valley G factor. And it turns out to be 29 in this situation on the left. Now compare this to the spin G factor, which is only 2. We have a much, much stronger splitting, 15 times bigger than the spin splitting. So this is really a huge splitting compared to the spin splitting. But we can tune this splitting, and this is very extraordinary in this system, by changing the geometry of the quantum dot. And this can be achieved with these 2 additional gates. We can make a larger quantum dot, and we can tune up this valley G factor from 29 to 74, which is a huge change. So people in the past tried, for example, also to tune the G factor for the spin in quantum dots. And you can typically change the G factor for spins by only a few %. Now here we can change the G factor for the valley by appreciable factors of 3, and I will later show you even changes of larger factors of 4 or 4.5 even. So we did a study of this valley G factor in a very systematic way as a function of quantum dot size. And you see in the schematic up here how we imagine the system to work. Using the left and right plunger gate, we can essentially change the density in the leads close to the quantum dot. And in this way, change also the tunnel barriers. And this in turn changes the extent of the wave function of the confined states in the quantum dot and makes it bigger from the left to the right. And as an experimental indicator of the quantum dot size, we take the charging energy. And as a function of charging energy, you see this valley G factor that we extract for the device. And you see that it has a very continuous dependence. When the charging energy gets smaller from the left to right, we essentially make the quantum dot larger in size, in geometrical size. And in this way, we tune the G factor up from 20 roughly to something like 90, which is a factor of 4.5 change in this valley G factor. So this is really a very promising number for later having qubits with very different excitation energies, because you can tune them to different G factors. And in this way, they get individually addressable in a multi-qubit architecture. The reason for the G factor change, the theory behind it, is related effectively to the topology close to the K point of this system. There is a finite Berry curvature which arises due to trigonal warping of the band structure close to the K point, for example. And the Berry curvature comes essentially with a magnetic moment of the quantum states close to the K point. And in this schematic here on the left, you see the magnetic moment associated with specific points in K space around the K point. And now, depending on the size of the quantum dot, and you see some wave functions here plotted, the wave function picks more or less contribution from this magnetic moment. And this magnetic moment is essentially coupling the states to the magnetic field and leads to the splitting of K and K prime states, because if the K states have a positive magnetic moment, as you see it here, the K prime states will have a negative magnetic moment and thereby shift in the opposite direction as a function of magnetic field. And you see the theory calculation essentially reproduces the order of magnitude of the numbers that we have for the valley G factor that we experimentally found for the valley G factor. They tried different geometries, circular dot, elongated dot along different directions, and get different numbers for the change of G factor with quantum dot size or elongation factor. Good. So with this, I'm almost at the end. Let me give you a brief outlook The tunability of this device also allows us to do what people have done in the past on carbon nanotubes, meaning to have a quantum dot in bipolar mode. Essentially, we can tune the system such that we can have a smooth transition from a whole quantum dot, which you've seen in my talk, to an electron quantum dot, tuning essentially through charge neutrality, which is here in the center where we have no charge carriers in the system. And this is also a pretty unique possibility in this graphene system. So with this, let me summarize my talk. I've shown you how we realize gate-defined quantum dots in graphene. This is published work that you can look up in PRX. And then I've shown you unpublished work on the tunable Valley G factor in these bilayer graphene quantum dots. And I've shown you that we have a factor of 4.5 tunability from 20 to 90 for this G factor. And at the end, I gave you a brief outlook on bipolar operation. So I think now we are in a situation with these graphene quantum dots that we can really start implementing qubits and qubit operations with these quantum dots, and that will be the future in our group on these systems. So I thank you for the attention, and I'm happy to answer questions if there's time.
Thank you, Professor In. We're a little bit tight on time, but we still have, I guess, 1 minute for 1 or 2 questions, please.
Okay, I can start. Yeah, thanks. That's really exciting, Thomas. Nice to see your latest work. I have a question on the data when you show the valley splittings in the perpendicular magnetic field, and then that data compared to the parallel magnetic field. I think I know the answer, but I still want to ask that. In this data, you pointed out the degeneracy at zero field. And now if you go to the next slide and you look at the zero field, there's no degeneracy, but there's at least 1 millivolt of splitting. So how is that?
Yeah, so in this plot here, we have removed essentially the charging energy between neighboring peaks. And this essentially shifts the resonances, the lowest 2 resonances in energy together to coincide in a single point. Of course, we don't know if this is a true degeneracy or if there is a small splitting, even a single particle splitting of levels, because we have no way experimentally to determine that. On the next slide, we did not remove this charging energy. We just show the values, and it's much clearer because otherwise they would sit on top of each other.
Yeah, so did I understand correctly that there is, in the lines, if you go back to the left, to the previous slide, so basically there is no degeneracy well, because of the charging energy, obviously there is no degeneracy in the dot. But when you remove the charging energy, all of these lines on the right, at least at finite field, we don't see degeneracy. So that there is no additional spin degeneracy on top of the valley degeneracy or valley sort of energy scale.
Yes, exactly. So for example, this spin state and this spin state, these are the same spins, the same values, sorry, it's K prime valley. They would have opposite spins, these 2 states, and they seem not to be degenerate at zero magnetic field. So there is some kind of spin polarization effect already going on. And we have a very clear understanding now about the 1 and the 2 electron or hole states in these quantum dots. We know exactly that the 2 electron ground state, for example, is a spin triplet state and a valley singlet state. Right, and we know the excitations also, which are then spin singlet and valley triplet states and so on. So we've investigated that in separate work, which I had no time to show.
Okay, but one more question, like in a single hole case, do you expect to see spin degeneracy at zero field for a single hole?
Yeah, that's a question at the end of geometry. So far, we cannot really tell from the data. It seems that there is a gap, but we also have measurements where we look at excited state spectroscopy, where we see the 2 spin states really splitting off from a degenerate case at zero magnetic field to a finite splitting at finite field, finite parallel field in the excited states. So we believe that at least in the dots we investigated so far, there is spin degeneracy at zero magnetic field for spin up and spin down.
Thank you.
Thank you so much, Professor In. Unfortunately, we don't have much time for other questions. It was a very interesting talk. Thank you. And so the next speaker is Benedikt Kratochwil from ETH Zurich. I believe he is from the same group as Professor In. Benedikt, please start.
Yes. Do you see my screen?
Yes.
Good. Okay, so I want first of all to thank the organizers for giving me the opportunity to talk today. And today I'm going to talk about the Cq3 Qubit, which is a charge qubit. This is what Cq stands for, implemented with a single electron charge, which is confined in a triple quantum dot. The 3, however, in this qubit name doesn't refer to the number of quantum dots we use to implement this qubit, but it refers to the third order sweet spot, which we achieve. Sweet spots are promising spots for increased qubit coherence, since the coherence effects due to charge fluctuations are minimized. But I will go deeper into that in the course of my talk. But before I start, I want to give you a quick overview of what I want to talk today. So in the beginning, I want to give a brief introduction into charge qubits and how we implement them in gallium arsenide, aluminium gallium arsenide heterostructures. It's a bit different than what Thomas showed you before for the graphene quantum dots. In the second part, I want to talk about this Cq3 qubit, the experimental data and the theory behind it. And I want to end with a small conclusion and an outlook. So whenever you want to define a qubit, you want to be able to define a 0 state and a 1 state. One way of doing this with a single electron charge is by having a potential landscape which has these 2 pockets, for instance, where you can find the electron either on the left, which we could refer to as a 0 state, or on the right pocket, referring to it as a 1 state. But how do we do this now in an actual semiconductor? So from our growers, the Wegscheider group at ETH, we get a gallium arsenide, aluminium gallium arsenide, a heterostructure which hosts a 2-dimensional electron gas at the interface of a gallium arsenide and an aluminum gallium arsenide layer. This basically symmetry breaking in the translational symmetry of this heterostructure causes these 2-dimensional states, which allows the electrons to flow in the x and y direction, but not in the z direction. By now taking this semiconductor to the clean room and fabricating a nanostructure of aluminum top gates like this on the top, which is, we can apply negative voltages to locally deplete this 2-dimensional electron gas even further. And then basically the electrons are confined on these 2 small islands, left and right here. And this is what we call a quantum dot. And if we take a more abstract view on this, we have a source which couples to the left and the right quantum dot, and then the right quantum dot couples to the drain. But by choosing correct gate voltages, we can basically decouple the source and drain contacts from this picture such that we don't have to worry about them. And we only worry about the tunnel coupling between the left and the right quantum dot. And because we are dealing with a real-life heterostructure, there is also noise. And in this kind of semiconductor qubits, we are always, the dominating noise source is charge noise, which can come from, for instance, charge traps, which are either located far away from this qubit or from these 2 dots, which causes the energy levels of these 2 dots to fluctuate in a very correlated manner, or they can be very close to our qubit, which would cause much more pronounced fluctuations in the dot closer to the trap. And these traps now can be filled with an electron which tunnels in and out on a very slow time scale. But if you now want to take a closer look at the energy structure of our quantum dot, it's best to think in these kind of energy levels, which we depict as the left energy level here and the right energy level here. They are detuned by a parameter which we call delta. And to give you some order of magnitude of this parameter delta, usually this is typical values for delta are in the range from several gigahertz. And for people who like to think more in electron volts, so 6 gigahertz is roughly 25 microelectron volts. And that equates roughly to 0.3 Kelvin. And this already tells you that in order to make these experiments, we have to go to dilution with richer temperatures. And if we now write down the Hamiltonian in this left-right basis, we have the detuning on the diagonal and the tunnel coupling on the off diagonals. And if we now diagonalize this Hamiltonian, it's easiest to think first in the zero tunnel coupling regime. Then the spectrum of this Hamiltonian just looks as follows. We get these two diagonal lines from the left state and the right. So for negative detuning, our left energy level is the lowest in energy, and for positive detuning, the right energy level is the lowest energy level and therefore our ground state. If we now turn on tunnel coupling, however, we get this avoided crossing. So we get the zero state in the blue line and the orange line showing the one state. And what we actually can measure in the experiment is the so-called qubit energy, which is the difference between these two states. It is a sort of parabola-like line shape. It's not a real parabola, but it comes close to it, which has a minimum at zero detuning, and the minimum is given by the value of the tunnel coupling, by 2 times the value of the tunnel coupling. If we now want to operate the qubit, for instance, at a delta of around 3 gigahertz, and we have noise coming from this charge traps, for instance, we see that a small change in delta gives us a big change in qubit energy and therefore causes dephasing of our qubit. However, if we operate the same qubit with the same order of same noise amplitude at zero detuning, we see that changes in delta only cause a very small fluctuations in energy, and therefore minimizing the dephasing of our qubit. So these points where the qubit energy has a minimum with respect to this detuning parameter is what we call a sweet spot. And if we now want to measure such a qubit dispersion in the experiment, in our group one method to do so is to use a resonator to probe this dispersion. And we usually have it far detuned from the energy of from the qubit energy. And from this, I want to show you a measurement from our collaborator, Pasquale Scarlino. So he has exactly this kind of double dot. And along this axis, he changes the detuning delta. And along this axis, he changes the drive frequency of the qubit while measuring the resonator. So if you initialize the resonator with the qubit in the ground state, you observe a resonance depicted by this red line when the qubit is in the ground state. And we probe the resonator slightly off resonance to increase sensitivity. If our drive frequency hits the qubit energy and therefore starts to excite our qubit, the dispersive interaction of the resonator and the qubit will lead to a slight shift of resonator frequency, and therefore a change in the reflected signal of our resonator, which basically causes this change of signal along this parabola. And if we now measure the qubit line width as a function of basically the slope, or also basically detuning, this is just a linear transformation, we see that the qubit line width is minimal at zero slope, so exactly in the sweet spot. And typical values for these qubit line widths in charge qubits in gallium arsenide are between 2 to 50 megahertz, which corresponds to T2 stars of 20 to 500 nanoseconds. And now maybe the question is interesting, can we gain any higher order sweet spot or any better protection from noise by going to a maybe more complicated system, as for instance a triple quantum dot? And the answer is yes. So if we now add a third quantum dot to the system, we still have this left and the right quantum dot, which are detuned by delta. So this black dotted line is just the energy reference with respect to which we measure the middle dot energy EM. And by adding this third quantum dot, we gain basically two more control parameters. So we now have to differentiate between left and right tunnel coupling, and we gain the middle dot potential. And there are also a lot of other different interesting operation points which we have already previously looked on in this triple quantum dot. For instance, the quadrupole qubit or the resonant exchange qubit, which is a spin qubit. But in this case, we want to focus on a single electron being confined in this triple quantum dot structure. And now this triple quantum dot even has a further advantage. Because we now have delta and EM as a parameter of our qubit, we now can start to differentiate where the noise comes from. Because noise coming from a far away noise source has a bigger influence on the detuning parameter delta, and noise coming from a closer charge trap affects the EM value much more. This basically gives us the opportunity to differentiate where the noise comes from. And as it was a common belief in theory that our noise sources are far away from our qubit, it is mostly attractive to protect our qubit from noise along the delta axis, which is exactly what we want to achieve. And the experimental setup now looks as follows. So we have the triple quantum dot here, and the quantum dots reside under these red dashed circles. The left quantum dot is attached to a squid array resonator. This has two advantages. The squid array resonator is of high impedance and therefore improves our coupling strength. And additionally, it allows us to change the resonator frequency by changing the flux through these squid loops. And we have the possibility to drive the qubit via the right quantum dot. And in order to make sure that we really just operate this qubit in the single electron limit, we use a quantum point contact to do charge sensing. And if we now basically measure the resonator signal, the reflected resonator signal, as a function of the delta and the M parameter, and we apply a constant drive tone, we can measure contour lines of constant energies. And what we find is that here we see this resonance appearing, which is very horizontal in delta, telling us that the qubit energy doesn't change as a function of delta for this configuration. And that's what we call the Cq3 point. But let me get one step back to show you what we actually change when changing the delta and the M. So what this plot shows is the qubit energy, so the difference between the ground and the first excited state, as a function of EM and delta. And by changing EM and delta, we shuffle the electron from the leftmost quantum dot in this area to the middle quantum dot here, or to the right quantum dot here. And along the black dashed lines indicated by 1, 2, and 3, always two of the electrochemical potentials of this triple dot are aligned. These are the charge transition lines. If we now plot these contour lines of constant energy, we find that for a value of EM, which is roughly -1/2 the tunnel coupling, we find that this qubit, the energy contour is flat in delta, meaning that we have a higher order sweet spot in delta. But I want to already note that it's not a sweet spot in EM. But as we assume that noise mostly affects our detuning axis because we are dominated by long-distance noise sources, This is okay. So now let's take a closer look at the energy level structure. So we fix the middle dot potential at this value of -1/2 the tunnel coupling, and look at the energy level structure as a function of delta. So the middle dot energy level doesn't change, and the left and the right energy levels, they are just crossing diagonally, as we already seen with the charged qubit in the with the double dot qubit in the zero tunnel coupling limit. If we now turn on the tunnel coupling, we again get these avoided crossings, and we observe that the curvature of the blue and these orange lines corresponding to the 0 and 1 state are very similar, leading to a very flat dispersion around zero detuning. In fact, it's flat up to third order, which we can prove mathematically. And for completeness, we also plot the transition energy of the first to the second excited state in the gray line. So in the first measurement, we show with two-tone spectroscopy, as I showed you before for the double dot qubit, then the measured dispersion relation of our qubit, and we notice two things. Number one is that it seems that our qubit is not as flat as we saw from theoretical calculations, but it's rather tilted a bit. This can be explained by the fact that we couple the resonator to the left quantum dot. This basically gives us a detuning-dependent coupling strength, where the coupling strength is higher for negative values of delta, and it gets lower the further we detune to positive delta. This slight tilt is also well covered by theory, which is shown by this red dashed line. Furthermore, we also observe that our qubit line width starts to increase when we start to approach this higher order sweet spot, which is against our intuition. If we measure the qubit line width as a function of decreasing drive power, we can extrapolate the qubit line width at this optimal or proposed operation point to be 53 megahertz, which is not good. But now let's further understand why we actually measure an increased qubit line width at this higher order sweet spot, which is against our intuition. So for that, we measured the qubit line width as a function of delta, and the plot of which you can find here. So here we change delta, and here we plot the qubit line width. And this was measured at a constant drive power, therefore the high line width, because we also have to include power broadening. And what we find is that we have a local maximum at this proposed qubit operation point, and two local minima roughly at delta equal to plus minus 6 gigahertz. To understand this now, it's very interesting to look at charge noise simulations on our system. And in the first simulation, we only introduce noise on the delta axis of 1 microelectron volt amplitude. So the middle dot energy doesn't change at all. And the simulation shows that we expect a low qubit line width around this sweet spot, and it starts to increase once we deviate from this sweet spot. But if we now assume the same magnitude of noise acting only on the middle dot and not changing the left and right energy levels at all, we find the following result. We find a local maximum at zero detuning and two local minima at roughly 6 gigahertz. These two local minima come from the fact that for plus or minus 6 gigahertz of detuning, we are in a sweet spot in EM. So to show this, when we operate the qubit in zero detuning, we are not in a sweet spot for EM. So we see a line cut of the qubit energy as a function, as a qubit energy as a function of EM at zero delta. And this is shown by this blue line. So we're not in a sweet spot here at this ideal operation point. But if we now look at the orange line, which shows a line cut at 6 gigahertz, we see that at the qubit operation point at EM optimal, we are actually in a sweet spot, giving rise to these two local minima left and right. And with this, basically, it's very straightforward to now construct, to fit this noise model. So the fit is shown here. So basically for this noise model, we include 1/f charge noise on both qubit parameters. And for completeness, we also include magnetic noise. But the order of magnitude for magnetic noise in this system is 2 orders of magnitude smaller than the influence of charge noise, so it's basically negligible. And what we find is that the noise amplitude, the ratio of noise amplitude on the detuning axis and on the EM axis is roughly 2, which is also in agreement with the quadruple qubit data we measured. And it tells us that against the belief of theory that we are dominated by long-distance noise sources, we also have a significant amount of short-distance noise sources which influence our qubit, and therefore it's not good to only protect this delta parameter, but actually it's more favorable to protect the delta and the EM axis with a sweet spot. Therefore, our qubit has a maximal line width at the proposed operation point because we are not protecting against noise on this axis. With that, I'm at the end of my talk and want to quickly conclude. So we showed an experimental realization of the Cq3 qubit. And what I showed you today is the dispersive interaction with a resonator. We also investigated resonant interaction and showed strong coupling to the resonator of this qubit. We measured a line width of 53 megahertz at the qubit operation point, which is not that good, but which can be explained basically by the lack of noise protection on the EM axis. And this all leads us to the conclusion that we are not only dominated by long-distance noise sources, but we also have to take care of short-distance noise sources in further qubit implementations. And as an outlook, I want to mention that it would be very interesting to investigate cases where the left and the right tunnel couplings are not equal, but very asymmetric. And what that would allow us to do is to now tilt this horizontal contour line of the qubit. And this would allow us to basically tilt the sweet spot along the axis of noise and therefore give us better qubit protection. And I want to also thank all my collaborators. So Klaus Ensil and Thomasin from Nanophysics Group at ETH, which give me the opportunity to work on this qubit. Andreas Landig and Janne Koski, who have worked on the experiments with me. We collaborate with the Wallraff Group at ETH, and Pasquale Scarlino. The material comes from the Wegscheider Group at ETH. And the theory, so the qubit was theoretically proposed by Mark Friesen from Wisconsin. And we have theoretical backup from Susan Coppersmith and Jose Carlos, who did all the noise simulations for us. With that, I'm at the end and want to thank you for your attention.
Thank you so much, Benedikt. So now it's time for the questions, please. Okay, in the case that there is no questions, let me again thank Benedikt for a wonderful presentation.
Thank you.
Oh, I guess we have one. No? Misha, do you have a question? Misha doesn't have a question. Anyway, thank you so much for a talk. It was really enlightening. And now the next speaker is my colleague, Michael Pirenstein, works at MIPT, Quantum, and Aalto University, and today he's going to talk about some multipartite entanglement. So I give my word to you, Michael. Please start.
Yeah, thank you. Thank you, Nikita, for a nice introduction. So let me share my screen. Okay. Okay, now it's full screen. Yeah, so today I'll present some results on multipartite entanglement in superconducting systems, and particularly for microwave quantum detection. And this work was done at Aalto University and mainly by my colleagues in the group of Professor Petri Hakanen. And so let me start. Here you can see the outline of the talk. And firstly, I will tell you about the motivation and why do we need multipartite entanglement, for what purposes. After that, I'll tell you about methods, how to generate multipartite entanglement in optical in both superconducting systems. After that, I'll cover a specific system that we are working on is Josephson parametric oscillators. And then I'll show you some experimental results on this device. And then I'll go to entanglement generation and show you some interesting numerical model that we're working on. And also I show you experimental results that actually verify this numerical model and this theory. And then I'll tell you about applications and mainly quantum detection using this Josephson parametric system. So why do we need multipartite entanglement? Actually, there are several applications. One of these is quantum communications or quantum cryptography, or in more general, this is called quantum internet. And there are several important initiatives, Europe in particular. For example, this QTech laboratory at Delft, QTech laboratory at Delft, and they have a huge project on quantum internet where they use these multipartite entanglement states. Also, there is certain interest in the distributed quantum computing, where we have several clusters of quantum processing units, and we can share the information between them and perform some efficient computing. And there's some interesting experiments. For example, there were recent the record superconducting link between two refrigerators in Wohlraff group in ETH. And also there is a distributed quantum sensing, quantum metrology, where we also can utilize entanglement in order to perform some state-of-the-art measurements using these systems. So the usual way how to generate entanglement state, it's optics, right? So quantum optics started this whole entanglement story. And the first proposition was how to generate entanglement in the optical system is to use some nonlinear medium. And in optics, this nonlinear medium is just some kind of nonlinear crystal with nonlinearity. And by applying some laser pump to the system, we can generate pair of entangled photons. And this is the usual way how you can generate pair of entangled photons. But if you want to generalize this, if you want to go further and create multipartite entangled state, the first thing that you can think about is to create a cascade of these nonlinear crystals. Use the second photon, which is entangled with the first one, as a pump for the second crystal, and then you can go so on and generate some kind of entangled cluster of photons where all photons are entangled and create some kind of this multipartite complex state. The disadvantage of this method is that it is really hard to control the structure of the entanglement, because when you work with some more couplings than systems than two particles, you have different structures of entanglement. You have inseparable states, you have genuine multipartite entanglement, and these things became difficult. And for the experimental realization, it was realized recently, the system of two nonlinear crystals, and it was possible to generate tripartite entanglement using this system. So for the drawbacks of this optical generation, as I said before, this is not a versatile system, so it is really hard to control entanglement structure. Moreover, if you manage to change this entanglement structure, it's often a really time-consuming refiguration of the optical setup, which can be difficult, for example, in some industry application when you need fast and accurate systems. And also the disadvantage of this approach is optical frequencies. So sometimes you need to work in a microwave range, in a microwave signals. For example, for the quantum radar, it is really good to work with the microwaves rather than optical signal. So how to create multipartite entanglement in superconducting systems? So we also need some kind of analogous for the nonlinear crystals. And in microwave signals, in microwave range, in superconducting circuits, it was proposed to use some kind of Josephson parametric system, which I will tell you a little bit later. But you can imagine just some kind of black box for now. It's a superconducting system. You apply the pump, and then you got yourself 2 entangled photons, which were generated from the vacuum state. And then you can use this entanglement as a for any purposes that you want to use them. So in order to generate more sophisticated, more, for example, tripartite entanglement, you can use several modes in one superconductor resonator, as it was done in Wilson's group in 2018. So they have used one resonator which has free modes, and what they have done is they create tripartite entanglement from these 3 modes, and also they manage to control this entangled state and manage to produce genuine tripartite entangled state. So it's like the most entangled state that you can achieve with these systems. So drawbacks obvious of this system that you have limited amounts of modes in your resonator, and it would be nice to have some system that you can easily scale up and work with multipartite entanglement in the future. So in our experiment, and also in theory, we consider Josephson parametric oscillator, which can be considered as a simple mechanical system, just a child on a swing. And when child sit down and stand up on the swing, it creates some excitations. And then analogous on the circuit, superconducting circuits, is just a parametric oscillator, which consists of the capacitor and inductance, which is a nonlinear element that consists of the Josephson junction. And this system is actually well studied, and it is often used as a Josephson parametric amplifier, because you can apply some signal, then apply the pump, and you create the conditions under where you can transfer the energy from the pump to your signal. And after that, you have the output signal, which is amplified. And these devices are used, for example, for qubits readout. And Jan from IQM told you about this the first day of the conference. And now, if we consider the same system, but we will not apply any input signal, then we will upconvert vacuum fluctuations. So we have a vacuum in this parametric oscillator, and by applying pump, we upconverting this vacuum, and it can be seen as a analogous of a dynamical Casimir effect, where we have moving mirror. So in order to mechanically excitate these vacuum fluctuations, you of course need really high speeds, something relativistics. But in our case, we can apply just really high frequency signals, and in microwaves, it's the gigahertz signal. So it's really great frequency range, and it is possible to upconvert vacuum fluctuations. And another interesting thing that these photons that are entanglement in these systems, they're generated in the system, they're entanglement because they're born from the same vacuum. So I will stop on this a little bit later. As I said before, this device was used as a Josephson parametric amplifier, and we also had a paper from the last year, which was published in Applied Physics Letters, where we used this same device, as I described before, as an amplifier, and for these purposes, we cool down it to millikelvin temperature. Then we use vector network analyzer in order to create input signal, and then we have output signal, which we analyze. and we show that this device is well tuned. So we can pick the frequency that we want to work on from 4 to 8 gigahertz, and then we can excitate parametric processes on each frequency, and therefore we show that our device is fully tunable, and we can see gain almost everywhere. And here you can see the experimental results on this device, where we change the pump parameters, the pump frequency and pump power. And change these parameters, we change also the process of parametric down conversion and also the gain profile. And we developed the theory based on the input-output theory that is well describes our experimental results. And also here you can see the gain profile and noise level of our amplifier, and we achieve almost 20 dB of gain with 100 megahertz bandwidth, which is a suitable device for the qubit readout. But next we want to use the same device as an entanglement generator. Yep. And for the entanglement generator, we do not apply any input signal, and we just have a vacuum in our Josephson parametric oscillator. Then if we apply single pump, we can generate pair of entangled photons in the same way as the optics. But when we apply several pumps, we actually can generate a cluster of entangled photons. And what is interesting is that one might expect that these down conversion processes can be regarded as random processes occurring independently on each pump. And in this case, the results would be simply the sum of these down conversion processes. However, it is not the case. And one can understand this by simple argument. That's supposed to look at the mode at a certain frequency, and then the quantum fluctuations of the mode will trigger 2-photon decay in both pumps, resulting in photons and the mirror image frequencies with respect to the half of the pump frequency. And these photons will necessarily be correlated, even if they originate from different pumps. And this due to the simple fact that they were born into existence by means of the same quantum fluctuations. And in order to analyze this process, we utilize the input-output theory and also Heisenberg-Langevin equation. So in order to characterize entanglement, we need to construct some kind of metric, and for these purposes, we used covariance metrics as an indicator. But in order to construct covariance metrics, we need to construct quadratures of the output signal. And if we consider the Hamiltonian of this driven system, where we have self term, and then the second term is for the quadratic dependencies, and this is driven of our parametric oscillator. And then we use this Hamiltonian in a Heisenberg-Langevin equation, and then apply input-output theory. We got ourselves these quadratures that we can then put into covariance matrices and then analyze the entanglement structure. And for the simple case, when we have just a single pump, we have a pair of photons. And when we have pair of photons, all equations can be solved analytically with no problem. And actually, these results that you saw here, they were the same equations were used and the same theory was used. But when we have several pumps, things becomes complicated. And of course, it is possible to solve this analytically, but it is a really headache, and it's much more efficient to develop numerical theory and develop numerical model, which can take into account all necessary correlations between these frequency modes. So, and here we consider tripartite entanglement only in two different cases. First, the first case we have only 2 pumps, and the second case we have 3 pumps. So it was really interesting to investigate the entanglement structure, and one of the most complicated entanglement state is the genuine entanglement, and it is really hard to analyze this state because, for example, common PPT criteria which was used for the bipartite state is not applicable there, and we need to look for some more sophisticated criteria. And actually, we found that one. It was published in 2014. And mainly it is a combination of some covariance matrices elements. And then it should be some inequality. So we have some kind of inequality which incorporates covariance matrices elements, and also some kind of convex optimization problem, which we use numerical methods in order to solve this. And numerical results shows that when we have only 2 pumps here, the dashed black lines, and we have 3 frequency windows here, then we can actually see genuine tripartite entanglement. So from this plot, everything that is not yellow indicates that we have tripartite entanglement. And here, for example, you can see the correlations, and you can see that 2 pumps generates not all correlations. So they trigger not all possible correlations, but 3 pumps can trigger all possible correlations. And therefore, this genuine multipartite entanglement is kind of a stronger entanglement. And when we pick the best point here, for example, you can see that we can break the inequality and reach the level where we have genuine tripartite entanglement with the 2 pumps as well as 3 pumps. And you can see that 3 pumps are actually better than 2 pumps. So also recently we applied some more advanced optimization techniques in order to analyze this inequality, and we got even better results. So it's even stronger than we thought previously. But this is a clear indicator that we can really achieve multipartite entanglement state in this parametric system. So for the experimental verification, we consider almost the same system as was used for the parametric amplifier experiment, but we incorporate 2 different parametric systems. And the first one was used as an entanglement generator, and it is a weakly coupled device. And the second one was used as a parametric amplifier that I talked before. And here, for example, you can see the design layout and the packaging of this device. So we forced to use parametric amplifiers because it improved signal to noise ratio, and signal to noise ratio actually is crucial in order to verify entanglement because signals are really weak. And also we use low temperature amplifier and room temperature amplifier. And after this chain of amplifiers, we have an IQ mixer, which helps us to analyze quadratures, particular quadratures of the signal. So the same device is here, you can see in here. And when we have RF signal, we used a local oscillator in order to separate the signal to I and Q quadratures. And we have recorded the data on the time range. Then we combine and process the signal in complex form. And after that, we perform a Fourier transform in order to move to the frequency domain. And on the frequency domain, we just cut the frequencies that we're interested in. And from these windows, we combine again and make it in the time domain. And then we can take each quadratures and construct covariance matrices elements. And this is just the experimental realization of the same approach that I told you before on the theoretical level. So for the real experimental results, when we apply single pump, we saw the gain because it works also as an amplifier, but also we took the covariance matrix and analyzed it. And you can see that off diagonal elements are higher than diagonal elements, which is a good evidence that we have something interesting is going on. And we also analyze it with the PPT criteria for the density matrix and the corresponding criteria for the covariance matrix, and verify that this is really entangled state. And also we managed to observe squeezing in this system. When we apply 2 pumps, now we have 3 frequency modes and can observe 3 tripartite entangled state. And we also analyze covariance matrix. And we plot the same dependencies of these criteria, of this inequality that should be broken in order to verify genuine tripartite entanglement as function of the pump power. And for example, here you can see that at first we have something close to the limit, then we go down. So here we got ourselves genuine tripartite entanglement, and then the pump is just too strong and we lose all entanglement there. But this is an experimental evidence and verification of the numerical theory that we built, that it is possible to observe this kind of genuine entanglement in Josephson parametric system. So now let's move to the applications. And actually, it is possible to use these systems as a quantum radar. And it is really interesting because quantum radar and microwave quantum sensing scheme can be used to calibrate, for example, quantum key distribution, or to perform ultra-sensitive measurements in biological, thermal, and mechanical systems, and also to improve low-power quantum detection when you need to apply low powers in order to detect an object. And here, for example, when we have distributed quantum sensing, mainly we have a network of sensors, and each sensor views the object from a different perspective, and they have the common entangled state. And this common entangled state actually boosts the performance of the metrological protocol for the detection. And it was shown theoretically that when we use entangled state rather than separable state, we can get yourself increase in sensitivity. And mainly when we have 3 different frequency windows, we can just take each frequency, and and photons at each frequency are sensors. And then we can distribute them spatially and perform a special metrological protocol. Also, efficiency of this entanglement network is reinforced by machine learning techniques, such as, for example, supervised learning, or where the model trains to make a prediction on labeled data. And there is an abundance task in supervised learning in which classical data are not available until they're acquired by sensors. And using entangled network can efficiently train the predictor by adjusting the parameters of sensing setup during the measurement process. And as I said before, each sensor in the network views the object from a different perspective, and the shared entangled probe state can improve performance of the estimating global parameters of the object that is under investigation. And this scheme is really interesting because you can adjust your metrological scheme to background that you have, and background is always noisy, and if there is some statistical noise, you can learn a model to avoid this noise and to improve the performance of the metrological scheme. Another way and more sophisticated that could also be used is to use reinforcement learning, where we have some smart agent which learn to change quantum radar network scheme in order to gain as much information as possible. And this is a little bit more complicated scheme, but it was shown in recent work in 2018 that it is possible to use some reinforcement learning agents in order to improve the performance of quantum algorithms, so optical setups. Particularly in this paper, they considered how to design an optical experiment using reinforcement learning agent. And it is also applicable here in a quantum distributed sensing. So that brings to the end of my talk. And let me just quickly summarize everything. So we proposed a novel method of the multipartite entanglement generation, and it is important that the structure of the entanglement is controllable, and we can also achieve genuine tripartite entanglement. And we expect that this method is also scalable. And also developed theory was verified by the experiment and also numerical simulations. And also we consider distributed quantum detection scheme, which is versatile and should be stable and scalable. And also, of course, we plan the experiment. So I believe that this is all. Thank you very much.
Thank you, Misha. So questions? Okay, I have a question. Oh, okay.
Okay, let me try one. There are several versions of quantum radar. So the one I sort of have in mind personally, which is rather difficult though, is sort of quantum holography, more or less. I mean, you actually you are interfering the echo with a control beam, and actually looks at things that way. But your version is not really to interfere an echo with a reference beam, is it? It's more like noise radar, or how do you interpret this?
Yeah, I believe it is more like a noise radar. But right now, actually, we are still, this is work in progress. So even theoretical work is in progress. But I believe that we aim to use the same protocol that was proposed in this paper, but it is a noise radar. Yeah.
Okay, thank you very much. Thank you.
Thank you.
So you only considered like the two-part, I mean, like bipartite and tripartite entanglement, right?
Yeah, that's right.
And have you considered anything besides that, like a larger number of entanglement?
Yeah, so actually now, thank you for the good question. Actually, now we have some theoretical results on a four-partite entanglement, if you can say, yeah, like four parties. And these theoretical results show that it is possible to generate this kind of entanglement in this system. But of course, experimental work is also in progress, and the experiment is really noise sensitive. So we really need to improve the readout scheme and also calibrate the noise in the system. And that, of course, will help us to scale this up.
Thank you.
In the this multi-entangled state that you want to generate here, I think what is needed is, I mean, I cannot look in this PRA because you don't have the full reference there. Exactly this kind of noise of enhancement of the signal to noise ratio that should be calculated. And the important question is whether it's more advantageous than of course, than the classical radar, but also with respect to the bipartite entanglement, whether this tripartite or four-partite is brings more signal to noise ratio.
Yeah, sure, but I believe that it was already shown theoretical. Then, when you have more parties in the entanglement states, you can increase the sensitivity, but at least theoretically. Of course, you're right that we need, of course, to compare it with the classical radars, and I believe that this is future plans for this work. Yeah, and sorry, yeah, I can send the whole.
Yeah, that would be useful. Yeah, send it to me at least. Thanks.
Thank you.
Okay, so if we don't have any further questions, let me thank you once again, Mikko, for a great talk. And we're moving to the next speaker. The next speaker is Professor Mikko Möttönen from Aalto University, known for his works in quantum computing and quantum computers. So, Professor Möttönen, please.
All right. thank you for the introduction, and thank you for the organizers of giving me the opportunity to present my work here. To begin with, I just want to ask you, do you now see the presenter view, or do you see the full slide view? Okay, great. So let me now start. So I want to talk about this result, which is on the archive. We put it there a couple of months back, but we haven't published it in the journal yet. So little changes are still possible. And we call it the photon-number-dependent Lamb shift. And I will walk you through why do we have such a maybe like a contradictory name to the people who know what Lamb shift is, but I think we have a good justification why we can do this. So this is work done mostly in my research group, and I want to thank all the group members. Now in the Corona time, we went outside and we had little gaps and we took the photo, but I think it turned out great. Well, not everybody came on site. Some were kind of remotely mentally present, but anyways, I think the picture came out great, and I also like to thank the collaborators. There's a kind of a mixed list of some collaborators. Not all of them are here, so don't be angry if your name is missing. I have highlighted Fabian here because of a nice story I want to tell you guys later on about the Lamb shift work we published last year, and obviously I want to thank all the funders. And I also like to thank the whole Center of Excellence for Quantum Technology. Here is 11 research groups in the center led by Jukka Pekola here in Finland, funded by the Academy of Finland. And also we have a quantum computer working group, and we are also working on quantum computer applications of the research that we are doing. Okay, but let's get to the chase. So first I will talk to you about Lamb shift and we'll give you a little introduction, and then about our first experiments on the Lamb shift, and then I will move on to the photon-number-dependent Lamb shift. All right. So classically, if you think about an atom, of course, an atom doesn't really exist classically because the electron would collapse into the nucleus. But let's imagine that you would have a classical system with charges, and if you have no electric field, external electric field in the system, the vacuum, the fact that you can have a field would not have any effect on your classical system. So, however, if you have a varying field, like if you shake a magnetic field or electric field, or of course put a static field as well, you would have an effect. And the varying field, especially even if the time average is 0, because of the nonlinearity of the atom or of your electrical system in a more general sense, because of the nonlinearity, that varying field, even though the time average would be 0, would have an effect. It would affect your system. Quantum mechanically, what is kind of the amazing thing about the Lamb shift is that actually in a quantum system of an atom or some other quantum systems, when you have an electromagnetic vacuum which has no photons in it, but the fact that your electrical degrees of freedom are coupled to this vacuum, that already gives rise to frequency shifts of your system, and those are called the Lamb shift. And there are also the effects from the varying field or finite temperature of your electromagnetic system. So you have photons at finite temperature in your electromagnetic environment, and those also give rise to frequency, or may give rise to frequency shifts, and those frequency shifts are called AC Stark shifts. So this is just like how we now define the Lamb shift and the AC Stark shift, and we differentiate between these two. Sometimes people don't always differentiate between the two, but we do, and that is kind of our definition. Okay, so about the history, the Lamb shift has been very important historically. even though it's a tiny correction to the energy levels of atoms, for example, but it has been an important one in the development of quantum mechanics. So back in the day, at 1947, Lamb and Rutherford, they made these amazing experiments measuring the excitation frequencies, basically the frequencies of the atomic orbitals in hydrogen. And back at that year, the Dirac equation was thought to be the most accurate description of atoms. And but the Dirac equation was saying that these two states, 2s half and 2p half, they are degenerate. And but in the measurement, they were not degenerate, as you can see here. And that was a mystery. And then there was this famous conference, and when coming back from the conference on the train, he realized that the shift is coming from the electromagnetic vacuum, from the fact that, so basically it is the Lamb shift as then defined later. So the fact that the hydrogen is coupled to the electromagnetic fields, even though there is no photons at these high energies there, it will give a shift. But what was important in that calculation actually was that he subtracted the zero frequency part of the Lamb shift, because otherwise it would be a divergent, very heavily divergent term, and would not predict the experiment. But what he realized is that even if the electron is not trapped in the potential of the atom, there is also a Lamb shift there, and the potential is basically zero frequency. So that's how he came, or the community then came up with the idea of renormalization. So let's subtract infinities out of infinities and get something that is finite, and Lamb shift was important there. So that's a little peek to the history, and I just want to make 3 points here that are important later on. In these first experiments, the spectrum of the electromagnetic environment was broad and dense. The whole vacuum. Of course, there's some container maybe that the system sees, but compared to the size of the atom, it's huge, and compared to the wavelength of the frequencies involved, it's very large, and so there is a broad and dense spectrum of modes in the environment. And well, because of the subtraction of the zero part of the shift, we started to call, or in the community, they started to call it the dynamic shift. So just to differentiate between the part where you have zero frequency contributions from the environment or from the trap, and non-zero frequency contributions. And also, by definition, as we defined, the Lamb shift is independent of the state of the electromagnetic environment, because it is the vacuum part, the part of the shift that comes from the vacuum. Okay, so these first 2 points we have accessed in a paper we published last year, and I will first talk about this paper and these results, and then I will give you our latest results on the dependence of the Lamb shift actually on the environmental temperature or the environmental photon number. But it's not in contradiction with Lamb's original experiments. It's not in contradiction. It is just something that it's we refine basically the model a bit, or the environment is more complicated, and that's why it happens. All right. There are nice experiments on the Lamb shift in superconducting circuits. For example, these three papers that I'm citing to here. But in these papers, you can see there's a transmon and a single mode, basically coupling of the transmon qubit to this the resonator here, and observing the shift coming to the transmon from the fact that the resonator mode is coupled to it. And that's already published a dozen years ago, and well understood phenomenon. There's another paper on the deep strong coupling regime where the Lamb shift is obviously then much bigger, and also the Lamb shift arising from many modes, but still discrete and well-defined peaks here. And these are all in superconducting circuits. And then I also highlight one paper where the phononic Lamb shift has been observed. So of course the phonon environment, in addition to the photon environment, is a similar bosonic environment, and it gives a similar shift as the photonic electromagnetic environment. All right. So in all of these cases, it was a bosonic environment, also giving rise to the shifts. And just to recap, previously a few narrowband modes have been studied in superconducting circuits. The dynamic versus static shift issue had not been discussed in these works. No temperature dependence was observed, and the qubit was tuned in these superconducting circuit experiments. And this is like a different type of way of studying the system as we have. So let me jump to our work. We have been developing these tunable environments for superconducting circuits, which basically means that instead of tuning the qubit or tuning the resonator, we actually tune the environment of the qubit or the resonator. And this way, we can, keep the system kind of ideally intact and just tweak the environment, and this way probe some of the effects, perhaps in an easier manner, more convenient manner that you would otherwise do. So we have two approaches called a tunable heatsink, where we have a static resistor and in a tunable resonator, and we can tune this resonator with a squid. And this basically, the resonator works as a bandpass filter, and then we can tune the sharp resonance in the environment, in and out of resonance with the system. However, we will not talk about this here today. Instead, we will talk about the quantum circuit refrigerator, which is an active system, so to say. We have tunnel junctions here, and when we turn on the voltage across the junctions, the tunneling of the electron starts to cool down or dissipate energy from the system. And here are some first papers on that, and actually we have combined also these two ideas in this paper here, but I will not go into more details on that. Instead, I will first give you an introduction of the QCR, and then I will talk about the Lamb shift results. So this is the image you saw already earlier. This is the setup in our experiment, and as you can see here on this tunneling graph here, so one arrow here denotes an electron or a quasi-particle that can tunnel from the superconductor to the normal metal through the insulating layer. And we can adjust this tunneling sort of rates by adjusting the voltage across the junction. But if you see at this voltage scale here, the electron cannot really tunnel horizontally here, because horizontal tunneling means that it doesn't get any other energy except the energy from the voltage source. But instead, if it grabs a photon from the resonator when it tunnels, this is called the photon-assisted tunneling, it does have enough energy. So this kind of channel opens up when we apply voltage to a right position. If the voltage is 0, this channel is also closed, and there is no tunneling. So this is the way we change the dissipation rate, by changing the voltage. We open up this channel of photon-assisted tunneling, and the system starts to dissipate when we crank up the voltage. So if we compare this scenario to the Lamb's experiment, Lamb had an electron system, a hydrogen atom, coupled to an electromagnetic environment made out of photons. Now, in our case, we have kind of a dual in a sense of this, because we have an electromagnetic system, which is the resonator. This is our system of interest. And the environment is composed of electron tunneling events. However, this electron tunneling environment can also be effectively described as a bosonic environment with effective parameters. So in a sense, it is not fully away from Lamb's experiment. Rather, it's actually quite close. Close to that in theoretical description. But let's go to the results. So here I plot the reflection coefficient from this capacitor here as function of the voltage, the bias voltage across a single junction, or actually no, across this SI-NIS junction pair here, and as function of probe frequency. So at 0 volts, you can see a dip in the absolute value of the reflection coefficient and the phase change from pi to minus pi. And this is a typical response of a harmonic oscillator that you would expect. However, when we increase the voltage, you can see that the resonance kind of bends, and there is a strange point where there's a 2 pi phase finding about. Actually, this point is a critical coupling point. You can see that the dissipation or the absorption of the resonator is going essentially to unity. So almost all radiation we put there is going to be absorbed. So this means that we are changing the quality factor of the resonator when we change the voltage. The bending means that we are changing the frequency of the resonator, and the bending is the Lamb shift, and the tunable coupling also comes there. So let's plot now the dissipation rate of the resonator as function of the voltage that we measure. And you can see that we can exponentially crank up the dissipation rate in the resonator when we increase the bias voltage, and then it saturates at high voltages. And we have 2 samples here, A and B, which has different frequencies to show you a little bit more data. And now the Lamb shift here basically would be calculated from the dissipation rate as a function of the frequency of the system, and we integrate over that, and then we have here the frequencies as well. And we have obtained this from 2 different approaches: a microscopic model based on the second order time-dependent perturbation theory, and then also from the Kramers-Kronig relations. And this is actually where Fabian's contribution steps in. And I just wanted to say that it was about 2 years ago when we had the last MIPT conference, and I was talking about these results, and Fabian was there, and he we started to talk about some modeling of the system, and then Fabian came out with this Kramers-Kronig relations, and that's how he got involved in this work. And we are a little bit in a similar situation actually today with the photon-number-dependent Lamb shift. There's more theory you could do to make the paper nicer. So if somebody's interested hearing on that more, what I have in mind, please contact me. Okay, but the Lamb shift from this theory and from the experiments, they seem to align quite nicely. So here you can see the dots, that is the experimental data. And then the dashed lines is the theory. And in sample A, we only took into account the dynamic shift. We didn't really see a need to take the static shift into account. However, in sample B, we could not explain the experimental data with the dynamic shift alone. And that's why we were saying that actually there is also static shift, and non-negligible static shift within the uncertainties of the experiments. We can observe it there. So the shape looks a little bit strange at first sight, but let me walk you through why this Lamb shift is first going down and then up. If we look at the environment, as I said, the environment is composed of these electron tunneling events, and as you can see, at 0 volts, the channel is high up in energy. And there's a peak in the density of states of the BCS superconductor here. And when we increase the voltage, this peak comes lower and lower in frequency. And when that peak is exactly corresponding to the frequency of our resonator, then we are actually here. So before that, there is a peak at higher frequencies, and those modes at higher frequencies in the environment are pushing down the frequency of the resonator. And then once we cross this point, the peak goes below the frequency, and then that's why it pushes it up. So if you remember, like, the modes tend to repel each other when they are coupled, the harmonic modes, and that's how you can explain this Lamb shift. The features in this Lamb shift. Okay, now people have started, is this really the Lamb shift? You know, you are measuring a system, you know, it is, you're probing it with classical microwaves and measuring just the frequency shifts. Is it an AC Stark shift? No, it's not an AC Stark shift, exactly because it's a linear oscillator. There's no AC Stark shift in a linear system. You know, if you have a linear system, you change electric field, you know, the frequency doesn't change. And there is, you know, the commutation relations between the ladder operators matters here when you do the microscopic derivation. Without those, it would not give us the right results. Okay, so now we have shown you that there's a broad and dense spectrum of environmental modes, and we can see the Lamb shift in such a system, in an engineered quantum system with the broad and dense spectrum of environmental modes. There's a dynamic shift involved. Well, how about the temperature dependence or the photon number dependence here? So to basically go now in the last 5 minutes to this topic, I just want to introduce you to the system. So instead of just a single sort of mode, we call the primary mode. So this is our sort of system depicted here. That is the system of interest, and that is now coupled with the environment. But the environment has also a bosonic, photonic part. So we call it the supporting mode. So, and here is a simplified electrical circuit diagram of our setup. And here you can see that we implement this as a single coplanar waveguide resonator with and having two modes involved. So basically, the fundamental mode is the primary mode, and the second mode, or the first excited mode is the supporting mode. And here now you can see that when we bias the system to low bias voltages, so that basically the channel is closed for the electrons to tunnel even if they absorb a photon from the primary mode, but the supporting mode is a higher frequency even, and if it gets a photon also from the supporting mode, then the electron can tunnel. So that's the idea. By exciting the supporting mode, by putting finite photon number now into our environment, we can induce dissipation into the system, and also perhaps we can induce Lamb shift, because that was the talk here about. And now here's the experimental data for the reflection coefficient at different powers of at the supporting mode at the sample. So this is low power. You can see that this looks very similar as a function of the bias voltage. It looks very similar to the scenario where we didn't have the supporting mode at all. But when we start cranking up the power in the supporting mode, you can see that actually there starts to be this kind of wiggling sort of features in the frequency. And also what I want to highlight here is that these kind of dips here. So first, you can see a dip arising rather close to the gap voltage here, where the Lamb shift anyway starts to kick in. And then you start to see them appearing closer. And this can be actually explained by the fact that the dip here corresponds to one photon absorbed from the supporting mode, in addition to the photon absorbed from the primary mode. So this is at such a voltage here. The upper scale shows you that the one photon from the supporting mode minus the gap voltage is right here, and that's the red line here. And then two photons is right there, and we can see them at the right voltages. So that's why we think that we are really seeing this multi-photon assisted tunneling, where the supporting mode is assisting, is cranking up basically the dissipation rate and the Lamb shift. Okay, but let us look at more closely about the damping rate, for example. So this again, at low supporting mode powers, this is basically corresponding to the old results. And then the new results, when we crank up the supporting mode power, you can see also oscillations actually in the damping rate that you didn't see in the previous image. And also we can see that the damping rate goes up when we increase the power. And now if we look at the shift, the frequency shift, you can see also these oscillations, and the solid lines correspond to the microscopic theory again, and there's a quite nice match between the theory and the results, because we have such many powers and we don't do individual fittings at each power or at each bias voltage, but there is only very few fitting parameters that basically gives all the theoretical lines for these plots, for both plots at the same time. And well, there is a little discrepancy here in the violet case, but I think that's because the the damping rate doesn't match either very well here. So there is still, of course, there's always optimization to do. But if you look at in general how this theory matches, we are very confident in this. We know what's happening. One of the nice features here that's at 0 volts, the lamp shift seems to be very small. But still we can control the dissipation rate by the supporting mode power. So this could be nice for example, qubit reset problem where you don't want to change the qubit frequency, but you just want to change the dissipation rate. However, I want to emphasize is that yes, there is a very large photon number dependent lamp shift. And this comes from the fact that we have now this kind of a hybrid environment where we have both bosons and fermions involved. We have the electrons are tunneling, and we have the bosons in supporting mode. So it is more complicated environment that typically is considered. Typically, you just considered a bosonic bath. You're happy theoretically, and you see, okay, the lamp shift doesn't depend on the number of photons or the environmental temperature. But here, the system is more complicated, and that's why we can see this photon number dependent lamp shift. Okay, I think I am now pretty much done. Here is just the summary of the results, and I'm happy to answer any questions that you might have.
Thank you, Professor Möttönen. Please ask your questions.
This was the first time I talked about the photon number dependent lamp shift, so it would be great to get some questions because I would know how to improve to the next talk. Or maybe everybody went to lunch already.
No, I'm still here. I'm Göran Windin. It's a stupid question. It's really marginal. Sorry. Go on in. Okay, I've done away with it. Just a stupid marginal question. I mean, this line profile you showed, that was sort of, to me, line profile, etc. So it's sort of what you get when a self-energy is doing things. Is there a sort of, would that formulation fit there for you or something, or it's just happens to be like that? I mean, it was in a previous slide on when you showed how the frequency dependence was before. There. Those kind of, to me, those line profiles, so, I mean, down there for the lamp shifts are typically found here. Line
oh, well, yes, you do get similar looking features, of course, in many many other systems as well.
Yep.
But I think this to me this seems to be well described by the fact that you have this peak here in the density of states. So well, you would have a similar feature, actually, a similar looking feature qualitatively if you just had a sharp resonance actually passing through, right? Is this kind of something that?
Yeah. Absolutely.
Yeah.
I agree.
Yeah.
Sure. That's the basis of it, but that's sort of a question of interaction energy between them and all that sort of thing. So it's just that when I see font profiles, then I get a feeling for what's going on immediately. Right?
Yeah. This of course, like there are many modes here in the environment. It's not just a single. So the total coupling strength gamma is kind of plotted it here, but then I'm not sure exact. I mean, maybe you could effectively say that there would be, just try to model it as a one mode, and then what would be the coupling to that mode? Maybe it would be quite close to gamma. I would.
It was just a marginal comment, right? I mean, it's,
okay.
Yeah. Okay.
Well, thank you.
Thank you.
Okay. Any other questions? Well, in the case that we don't have any other questions, I gotta say that we will have 2.5 hours break. And after that, we will resume at 4:30, and we'll have 2 more talks. Thank you so much, Professor Möttönen. It was a very great talk. Thanks, everyone. Have a good lunch.